Hello everybody, and today is our 30th Neuroanatomy stream. I couldn't express how happy I am right now because of this milestone. But surely, even when I finish this book, I don't think that um, it's the it will be the end. But I'm looking for I mean, when I finish this book, it's not the end. In fact, I think it's very likely that I'll be reviewing more neuroanatomy books. But let's see whether time allows for it. Okay, so we are at the Insula and Sylvian Fissure. Here we will complete our walk through the Cerebral Gyri and Sulci with a drawing of the Insula and the Sylvian Fissure. First, to get a good look at the Insula, draw a coronal view of a cerebral hemisphere. Indicate that the Insula, also known as the island of Ryle, lies deep within the brain under the cerebral folds, the opercula. The superior opercula comprise the frontal and parietal opercula. The inferior operculum is the temporal operculum. Now let's take a look at the insula in sagittal view. Draw a lateral face of the cerebral hemisphere, but carve out the center of the hemisphere. Indicate that the circular sulcus circumscribes the insula, except in the anteroinferior region at the Limen Insulae, the insular apex. Where is that? Next, show that the central sulcus extends through the insula, but carve out the center of the hemisphere. Indicate the circular sulcus circumscribes the insula. Oh, okay. I get it. I understand. Okay. Circumscribes the insula. Okay. Now start a table. Central sulci. Label the posterior short insular gyrus. Okay. Anterior to the short insular sulcus, label the anterior short insular gyrus. Now within the posterior lobule, draw the post-central sulcus. In between it and the central sulcus, label the anterior long insular gyrus, and posterior to it, label the posterior long insular gyrus. The insula has widespread intracortical connectivity, including connections to the hypothalamus, thalamus, cortical sensory association areas, auditory cortex, and the limbic system. It has been shown to play a role in pain modulation, appetite, awareness of visceral sensation, anxiety and emotion, socialization, and auditory processing, and much more. Next, let's learn the detailed anatomy of the Sylvian fissure and its related structures. First, draw the undersurface of the brain, but exclude the anterior temporal lobe. Define the region surrounding the chiasma opticum as the anterior perforated substance, which is perforated by short branches of the proximal middle cerebral artery. Next, label the internal carotid artery just lateral to the chiasma opticum. Then show that the proximal middle cerebral artery, the M1 branch, originates from the internal carotid artery within the cisterna of the vallecula cerebri, also known as the cisterna carotica, and passes laterally within this cistern through the deep or basal portion of the Sylvian fissure between the frontal and temporal lobes. As the Sylvian fissure wraps around to the lateral convexity of the brain, the related cisternal space becomes the cisterns of the lateral cerebral fossa. Exactly where this cisternal transition occurs is inconsistently defined. Now, let's continue with the lateral face of the Sylvian fissure. First, draw the anterior-inferior division of the Sylvian fissure. At its midpoint, draw a V for the rami. The lower arm of the V is the anterior horizontal ramus, and the upper arm is the anterior ascending ramus. Indicate that this rami subdivide the inferior frontal gyrus into the pars orbitalis, pars triangularis, and pars opercularis. Next, let's draw the posterior superior division of the Sylvian fissure. At the distal end of the central sulcus, draw the horizontally directed posterior horizontal ramus. Then complete the Sylvian fissure with the posterior ascending ramus. Indicate that the supramarginal gyrus caps this ramus. Note that the posterior descending ramus also exists, which lies along the vertical plane of the posterior ascending ramus. We leave it out for simplicity. With this Sylvian fissure anatomy defined, return to the lateral face of the insula to further illustrate the various cerebral opercula in accordance with Neuroanatomy description. Label the optical operculum inferior to the anterior horizontal ramus of the Sylvian fissure. Frontal operculum in between the anterior horizontal and anterior ascending Sylvian fissure rami. Frontal operculum. Parietal operculum parietal operculum in between the anterior descending and posterior Sylvian fissure rami, and the temporal operculum inferior to the posterior ramus of the Sylvian fissure. The temporal operculum is formed from the transverse temporal gyri, Heschel's gyri, and the superior temporal gyrus. Okay, now we can draw, I think. Do you have any questions or anything? Let's see if chat has any questions. No? Nothing? That's good. I think should wait for the ink to dry for a while. Because if you touch this thick black ink, it will splatter everywhere. Um, so house expert, yeah. To get a little recap, earlier on the 1st of May, we had some kind of festival. It's called May Day, and in Oxford they call it a May morning. In 6 a.m., the crowd would gather to see the Magdalen College Choir performing what I'm calling a mini church service or so. I have it recorded in my channel. You should check it. And then after the service ends, which lasted around half an hour, you can go to the city center or the Radcliffe camera and see or participate in Morris dancing. As for me, I had my breakfast in the Hartford College. Supramarginal gyrus. I got some. Sylvian fissure. Okay, we can do Broadman areas, but we should go to the bathroom for a while. I will return in 1 minute. Okay, let's go. Broadman areas. Here we will learn select Broadman areas, which Corbinian Broadman published in 1909. He distinguished 52 different cytoarchitectural areas. Each area or group of areas subserves a unique function. On the lateral face of the cerebrum, draw the precentral, central, and postcentral sulci, and then the Sylvian fissure with its anterior horizontal and anterior ascending rami. Also include the lateral parieto-temporal line. Let's see. Where is my glasses? Where's my glasses? I thought I had it. Oh, On the medial face, draw the paracentral, central, parieto-occipital, and calcarine sulci, and then draw pars marginalis and the cingulate sulcus, and demarcate a line just above it. Paracentral. Okay. pars marginalis. Now label Broadman areas 3, 1, 2 within the post-central and posterior paracentral gyri. From anterior to posterior, they constitute the primary sensory area. Then label area 4 within the Now label, I have to repeat it, but later. Then label area 4 within the precentral and anterior paracentral gyri. Indicate that it is the primary motor area. Within the primary motor and sensory areas, cortical representation of the face and body is somatotopically arranged in what is referred to as the homunculus. Now label area 6 in front of area 4 in the posterior frontal lobe. Indicate that it lies in the posterior frontal lobe and that it comprises the following motor areas. On the lateral hemisphere, area 6 is called the premotor area. It lies in the anterior precentral gyrus and posterior superior and middle frontal gyri. And on the medial hemisphere, area 6 is called the supplementary motor area. It lies in the medial aspect of the superior frontal gyrus. The premotor and supplementary motor areas help assemble complex motor programs. Next, label area 8 in front of area 6 in the anterior frontal lobe. Indicate that it lies in the anterior frontal lobe and that the most notable feature of area 8 is that on its lateral surface, it contains the human homologue to the rhesus monkey frontal eye fields, the animal model for human eye movements. In humans, however, volitional control of eye movements is derived from the anterior wall of the precentral sulcus and portions anterior wall of the precentral sulcus. Okay. And portions of many additional disparate Broadman areas, including areas 4, 6, 8, and 9. Now label area 44 in the pars opercularis and area 45 in the pars triangularis of the inferior frontal gyrus. Indicate that together, areas 44 and 45 make up broadcast area, the language output area. Next, demarcate the superior temporal gyrus and then peel it back and label areas 41 and 42 in the transverse temporal Heschel's gyri. These gyri form the primary auditory cortex. Then label area 22 in the superior temporal gyrus. Indicate that in the posterior region of area 22 and area 39, the angular gyrus, lies Wernicke's area, the language reception area. Now, within the occipital lobe, on the medial surface, indicate that area 17 lies on the banks of the calcarine sulcus, and on the lateral surface, show that it lies at the occipital pole. Indicate that area 17 is the primary visual cortex. Now, on the medial face, show that area 18 lies above and below area 17. Then show that area 19 lies above and below area 18. Indicate that area 18 lies in the occipital lobe and is the secondary visual cortex. Next, indicate that area 19 lies in the occipital lobe and is the tertiary visual cortex. Then, on the lateral face, show that area 18 lies anterior to area 17 and that area 19 lies anterior to area 18. Next, antero-inferior to area 8, along the surface of the lateral and medial faces of the cerebrum, from superior to inferior, label areas 9, 10, and 11. Then, in between area 45 and area 18, label area 46. Then, beneath area 46, label area 47. And finally, in the anterior cingulate gyrus, label area 24. These areas form the prefrontal cortex, which is subdivided into dorsolateral frontal, dorsolateral prefrontal, orbitofrontal, and anterior cingulate medial frontal cortices. Each subdivision governs a discrete cognitive domain. Although the exact anatomy of these divisions is inconsistently defined, there is consensus regarding their functions. Indicate that together, areas 9, 46, and a portion of area 10 form the dorsolateral prefrontal cortex. Together, areas 11 and 47 and a portion of area 10 form the orbitofrontal cortex. Indicate that area 24 comprises the anterior cingulate cortex. Indicate that, as noted previously, dorsolateral prefrontal cortex mediates executive function, task sequencing. Injury here results in organizational deficits. Orbitofrontal cortex governs social behavior. Damage here results in impulsivity. And anterior cingulate medial frontal cortex mediates motivation. Injury here results in a lack of motivation, abulia. Okay, now we have to repeat it thrice. Because I believe that this will show in some kind of exams. Here we will learn select Broadman areas, which Corbinian Broadman published in 1909. He distinguished 52 different cytoarchitectural areas. Each area or group of areas subserves a unique function. On the lateral face of the cerebrum, draw the precentral, central, and postcentral sulci, and then the Sylvian fissure with its anterior horizontal and anterior ascending rami. Also include the lateral parieto-temporal line. On the medial face, draw the paracentral, central, parieto-occipital, and calcarine sulci, and then draw pars marginalis and the cingulate sulcus, and demarcate a line just above it. Now label Broadman areas 3, 1, 2 within the posterior, postcentral, and posterior paracentral gyri. From anterior to posterior, they constitute the primary sensory area. Then label area 4 within the precentral and anterior paracentral gyri. Indicate that it is the primary motor area. Within the primary motor and sensory areas, cortical representation of the face and body is somatotopically arranged in what is referred to as the homunculus. Now label area 6 in front of area 4 in the posterior frontal lobe. Indicate that it lies in the posterior frontal lobe and that it comprises the following motor areas. On the lateral hemisphere, area 6 is called the premotor area. It lies in the anterior precentral gyrus and posterior superior and middle frontal gyri. On the medial hemisphere, area 6 is called the supplementary motor area. It lies in the medial aspect of the superior frontal gyrus. The premotor and supplementary motor areas help assemble complex motor programs. Next, label area 8 in front of area 6 in the anterior frontal lobe. Indicate that it lies in the anterior frontal lobe and that the most notable feature of area 8 is that on its lateral surface it contains the human homologue to the rhesus monkey frontal eye fields, the animal model for human eye movements. In humans, however, volitional control of eye movement is derived from the anterior wall of the precentral sulcus and portions of many additional disparate Broadman areas, including areas 4, 6, 8, and 9. Now label area 44 in the pars opercularis and area 45 in the pars triangularis in the inferior frontal gyrus. Indicated together, areas 44 and 45 make up broadcast area, the language output area. Next, demarcate the superior temporal gyrus and then peel it back and label areas 41 and 42 in the transverse temporal gyri, Heschel's gyri. These gyri form the primary auditory cortex. Then label area 22 in the superior temporal gyrus. Indicate that in the posterior region of area 22 and area 39, the angular gyrus lie Wernicke's area, the language reception area. Now, within the occipital lobe, on the medial surface, indicate that area 17 lies on the banks of the calcarine sulcus, and on the lateral surface, show that it lies at the occipital pole. Indicate that area 17 is the primary visual cortex. Now, on the medial face, show that area 18 lies above and below area 17. Then show that area 19 lies above and below area 18. Indicate that area 18 lies in the occipital lobe and is the secondary visual cortex. Next, indicate that area 19 lies in the occipital lobe and is the tertiary visual cortex. Then on the lateral face, show that area 18 lies anterior to area 17 and that area 19 lies anterior to area 18. Next, antero-inferior to area 8, along the surface of the lateral and medial faces of the cerebrum, from superior to inferior, label areas 9, 10, and 11. Then in between the area 45 and area 10, label area 46. Then, beneath area 46, label area 47. And finally, in the anterior cingulate gyrus, label area 24. These areas form the prefrontal cortex, which is subdivided into dorsolateral prefrontal, orbitofrontal, and anterior cingulate, medial frontal, cortices. Each subdivision governs a discrete cognitive domain. Although the exact anatomy of this division is inconsistently defined, there is consensus regarding their functions. Indicated together, areas 9, 46, and a portion of area 10 form the dorsolateral prefrontal cortex. Together, areas 11 and 47 and a portion of area 10 form the orbitofrontal cortex. Indicate that area 24 comprises the anterior cingulate cortex. Indicate that, as noted previously, dorsolateral prefrontal cortex mediates executive function, task sequencing. Injury here results in organizational deficits. Orbitofrontal cortex governs social behavior. Damage here results in impulsivity. An anterior cingulate medial frontal cortex mediates motivation. Injury here results in a lack of motivation, abulia. Okay, once again, and then we will draw. Broadman areas. Here we will learn, select Broadman areas, which Corbinian Broadman published in 1909. He distinguished 52 different cytoarchitectural areas. Each area or group of areas subserves a unique function. On the lateral face of the cerebrum, draw the precentral, central, and postcentral sulci, and then the Sylvian fissure with its anterior horizontal and anterior ascending rami. Also include the lateral parietotemporal line. On the medial face, draw the paracentral, central, parietoccipital, and calcarine sulci, and then draw pars marginalis and the cingulate sulcus and demarcate a line just above it. Now label Broadman areas 3, 1, 2 within the postcentral and posterior paracentral gyri from anterior to posterior. They constitute the primary sensory area. Venable area fall within the precentral and anterior paracentral gyri, indicate that it is the primary motor area. Within the primary motor and sensory areas, cortical representation of the face and body is somatotopically arranged in what is referred to as the homunculus. Now label area 6 in front of area 4 in the posterior frontal lobe indicate that it lies in the posterior frontal lobe and that it comprises the following motor areas. On the lateral hemisphere, area 6 is called the premotor area. It lies in the anterior precentral gyrus and posterior superior and middle frontal gyri. And on the medial hemisphere, area 6 is called the supplementary motor area. It lies in the medial aspect of the superior frontal gyrus. The premotor and supplementary motor areas help assemble complex motor programs. Next, label area 8 in front of area 6 in the anterior frontal lobe. Indicate that it lies in the anterior frontal lobe and that the most notable feature of area 8 is that on its lateral surface, it contains the human homologue to the rhesus monkey frontal eye fields, the animal model for human eye movements. In humans, however, volitional control of eye movement is derived from the anterior wall of the precentral sulcus and portions of many additional disparate Broadman areas, including areas 4, 6, 8, and 9. Now label area 44 in the pars opercularis and area 45 in the pars triangularis of the inferior frontal gyrus. Indicate that together, areas 44 and 45 make up broadcast area, the language output area. Next, demarcate the superior temporal gyrus and then peel it back and label areas 41 and 42 in the transverse temporal Heschel's gyri. These gyri form the primary auditory cortex. Then label area 22 in the superior temporal gyrus. Indicate that in the posterior region of area 22 and area 39, the angular gyrus, lies Wernicke's area, the language reception area. Now within the occipital lobe on the medial surface, indicate that area 17 lies on the banks of the calcarine sulcus. And on the lateral surface, show that it lies at the occipital pole. Indicate that area 17 is the primary visual cortex. Now on the medial face, show that area 18 lies above and below area 17. Then show that area 19 lies above and below area 18. Indicate that area 18 lies in the occipital lobe and is the secondary visual cortex. Next, indicate that area 19 lies in the occipital lobe and is the tertiary visual cortex. Then, on the lateral face, show that area 18 lies anterior to area 17, and then area 19 lies anterior to area 18. Next, antero-inferior to area 8, along the surface of the lateral and medial faces of the cerebrum. From superior to inferior, label areas 9, 10, and 11. Then in between area 45 and area 10, label area 46. Then beneath area 46, label area 47. And finally in the anterior cingulate gyrus, label area 24. These areas form the prefrontal cortex, which is subdivided into dorsolateral prefrontal, orbitofrontal, and anterior cingulate medial frontal cortices. Each subdivision governs a discrete cognitive domain. Although the exact anatomy of this division is inconsistently defined, there is consensus regarding their functions. Indicate that together, areas 9, 46, and a portion of area 10 form the dorsolateral prefrontal cortex. Together, areas 11 and 47 and a portion of area 10 form the orbitofrontal cortex. Indicated area 24 comprises the anterior cingulate cortex. Indicate that, as noted previously, dorsolateral prefrontal cortex mediates executive function or task sequencing. Injury here results in organizational deficits. Orbitofrontal cortex governs social behavior. Damage here results in impulsivity. And anterior cingulate, medial frontal cortex, mediates motivation. Injury here results in a lack of motivation, abulia. Okay. Broadman areas. It may be too early to say this, but I think this is the main course of the book. Body. Three, one, two. Postcentral and postparacentral gyri. Primary sensory area. 4. Precentral and anterior paracentral gyri. Primary motor area. 6. Posterior frontal lobe. Motor areas. 3. And supplementary. 8. Anterior frontal lobe. Rhesus monkey frontal eye field. 44, 45. Broca area. Language output area. 41, 42. Transverse temporal Fissure. Primary auditory cortex. 22 and 39. Wernicke's area. Language reception area. 17. Packarin Sulcus. Primary visual cortex. Okay. Let's see. Lobe. Secondary visual 19. No. 39. 1. 46. 9. 46. Torso lateral prefrontal cortex. Executive function. 11:47. Orbital frontal cortex. Social behavior. 24. Anterior cingulate cortex. Motivation. Okay. Okay, I will attempt to draw it from memory now. So I will turn this off and turn this off. Okay, let me see if I can pass through this. I might be. Okay. Okay, let's see. Prefrontal, or what the name? Dorsolateral. Okay, I think I have memorized it by now. We can move on to the next drawing. Don't miss the main course, because the main course is the main food. Cerebral cortical histology. Here we will learn the neocortical layers and the histology of neurons and glia. To begin, let's address the different cerebral cortical classifications. Indicate that cerebral cortex can be classified into one of three distinct histological patterns: allocortex, mesocortex, and neocortex. First, draw a sagittal view of the brain. Indicate that allocortex is phylogenetically old, comprising as few as 4 layers up to 5 layers. Now draw the allocortex as the olfactory cortex, uncus of the parahippocampal gyrus, which is its medial thumb, and the hippocampus, and associated dentate gyrus. Okay. Uncus of the parahippocampal gyrus and the hippocampus, and associated dentate gyrus. Indicate that allocortex further subdivides into paleocortex. Here the olfactory cortex, and archicortex, ancient cortex. Here the hippocampus. Next, indicate that neocortex is also referred to as isocortex, is phylogenetically new and comprises 6 histologically distinct layers. Draw an outline of the brain to represent the neocortex. It constitutes roughly 90% of the cerebral cortex. Finally, indicate that mesocortex represents transitional cortex between neocortex and allocortex. Show that it comprises the cingulate gyrus, and the remainder of the parahippocampal gyrus. Mesocortex further subdivides into periallocortex and proisocortex, and periallocortex further subdivides into peripaliocortex and periarchicortex. Now let's illustrate a basic diagram of neurons and glia. Write that, in addition to blood vessels, the brain comprises two main cell types, neurons and their supporting cells, glia. The human brain has at least 100 billion neurons. We categorize neurons into two types. The first type is pyramidal cells, which are 10 to 18 micrometer (μm) in diameter, (μm) in diameter, and are shaped like a flask with a single thick cortically oriented apical dendrites and multiple basal dendrites. One important pyramidal cell type is the Betz cell, which lies within the primary motor cortex. The second type is a non-pyramidal cell. These non-pyramidal cells, which are much smaller, they are 5 to 15 μm in diameter. The term non-pyramidal cell is used interchangeably with the term stellate or granule cells, but other non-pyramidal cell types exist, which include basket cells, fusiform cells, horizontal cells of Kajal, Bertinotti cells, and neurogliaform cells. Next, let's look at the histology of neurons and glia at high resolution. Identify the large neuron, then an astrocyte. Next, locate an oligodendrocyte, which we identify by their small, condensed, round nucleus and a clear cytoplasm, an artifact of processing, the so-called fried egg appearance. Now let's draw the features of the neuron that help us identify it. Its large basophilic cytoplasm. Large nucleus with diffuse chromatin. Prominent nucleolus. Neuronal process. Okay. Now, to better visualize the dendrites and axons, let's look at the stage section of the cerebrum. Identify a glial cell. Identify a neuron and specify a dendrite and the cell's axon. Then indicate neuropil, which is the fibrillary amalgamation of dendritic processes and axons that constitute the bulk of the slide. Lastly, let's label the 6 cytoarchitectural layers of the neocortex from outside to inside. Layer 1 is the molecular or plexiform layer. Indicate that it is primarily a nerve fiber layer, meaning it is cell sparse and predominantly comprises axons and dendritic processes. Nerve fiber layer, plexiform. Layer 1, molecular. Okay, flexiform. Layer 2 is the external granular layer, which contains non-pyramidal cells of 5 to 15 μm and relatively few small pyramidal cells. External granular. Okay, layer 3 is the external pyramidal layer, which predominantly contains pyramidal cells of varying size, 10 to 80 μm. Also, layer 3 is sparsely populated with non-pyramidal cells. Layer 4 is the internal granular layer, which is densely packed with non-pyramidal cells. Layer 4 contains the horizontally oriented external band of Baechler, a prominent thalamocortical nerve fiber layer. In the primary visual cortex, this nerve fiber band is called the line of Xury. Next, layer 5, the internal pyramidal or ganglionic layer, contains the largest pyramidal cells, most notably the Betz cells of the primary motor cortex, the major cortical motor neurons. The horizontally oriented internal band of Baechler lies deep within this layer. Lies deep. Okay, so it also layer 4 and 5 has Baechler. Layer 6, the multiform or fusiform layer, contains a wide variety of pyramidal and non-pyramidal cells that show the underlying white matter. Although the specific cellular constitution and nerve fiber density of each histological layer vary across the cerebral cortex, certain areas of similarity exist, which we know as the Broadman areas. Okay, This is the architecture that I'm interested in replicating using 3D printing and cell culture. But I don't know what it takes to be able to make this because when you grow a spheroid, yeah, it's a spheroid. You can't control the other parameters or which Broadman area do you want this portion of spheroid grow into. It keeps making embryonic brains. What is this? Instagram is cut off. It's getting more yabai and yabai. No problem. Just don't say reply to our message. It's much clearer. You are forcing your ideas. Don't make it whole perfectly. You'll regret. You'll regret if you make it perfectly. Okay, now we have a break for about 10 minutes because I have to do my dishes. I'll let you know when it's done. Cerebellar Anatomy. Here we will use a flattened perspective of the cerebellum to learn the cerebral anatomic lobes, zones, and functional modules. In essence, we peel back the anterior cerebellum so that the anterior lobe ends up at the top of the diagram and the flocculonodular lobe lands up at the bottom. Draw the corpus cerebelli, which constitutes the bulk of the cerebellum. It comprises the anterior lobe, flocculonodular lobe, corpus cerebelli. Draw the corpus cerebelli, which constitutes the bulk of the cerebellum. It comprises the anterior and posterior cerebellar lobes. Indicate that on the right we will draw the cerebral lobes, and on the left we will draw the cerebellar zones. Show that the primary fissure separates the corpus cerebelli into an anterior one-third, which forms the anterior lobe, primary fissure, and then posterior two-thirds, which forms the posterior lobe. Next, below the corpus cerebelli, draw the propeller-shaped flocculonodular lobe. Label its nodule in midline and flocculus out laterally. Show that the posterolateral fissure separates the corpus cerebelli from the flocculonodular lobe. Now let's draw the cerebellar zones. Indicate that the midline cerebellum is the vermis, which means worm-like. Then lateral to it, indicate the paravermis, also known as the intermediate zone, and lateral to it label the hemisphere, also known as the lateral zone. Next, let's learn the functional modules. The vestibulocerebellum is phylogenetically the oldest portion of cerebellum and is referred to as the archicerebellum. It is derived from the flocculonodular lobe and the anterior tip of the vermis, lingula. Anterior tip of the vermis, lingula. Archicerebellum, flocculonodular lobe, and the anterior tip of the vermis, the lingula. The vestibulocerebellum receives its name because of its midline vestibulo and olivocerebellar fibers, which project to the deep medial lying cerebellar fastigial nuclei. It is important for equilibrium and eye movements. The spinocerebellum is phylogenetically the next oldest and is referred to as the palaeocerebellum. It is derived from the anterior lobe and the majority of the vermian and paravermian posterior lobe. The spinocerebellum receives its name from its major input fibers, the Spinocerebellar Tracks. It plays a major role in postural stability. The pontocerebellum is phylogenetically the newest portion of the cerebellum and is referred to as the neocerebellum. It is derived from the remainder of the posterior lobe. The pontocerebellum receives its name because it acts through the cortico-pontocerebellar pathway. It is geared toward fine motor movements, which are typically goal-oriented. Now let's address a couple of clinical correlates. Indicate that in acute alcohol intoxication, the entire cerebellum is affected. Vestibulo, spino, pontocerebellum. Use this example to learn the major deficits associated with with each functional module. Nystagmus occurs from toxicity to the vestibulocerebellum. Truncal ataxia occurs from toxicity to the spinocerebellum, and incoordination occurs from toxicity to the pontocerebellum. Next, note that in alcoholic cerebellar degeneration, the pathology is predominantly restricted to the anterior superior cerebellar vermis. Because of this restricted area of injury, truncal ataxia is sometimes the sole deficit. Spinocerebellum. Okay. We may miss the exam finding if we fail to ask our patients to stand during the exam. Truncal ataxia. Oh. Now regarding the general somatotopic organization of the cerebellum, note the following. Unilateral cerebellar lesions affect the ipsilateral side of the body. The midline cerebellum plays a role in posture, whereas the lateral cerebellum assists in fine motor, goal-oriented skills. For instance, to stand upright, you need the midline cerebellum, and to play the piano, you need the lateral cerebellar hemispheres. Lastly, let's draw the somatotopy of the cerebellum. Redraw a cerebellum with a flattened perspective. Divide the anterior and posterior lobes at the primary fissure. Shade the anterior lobe, posterior lobe, and flocculonodular lobe. Show that the somatotopic limb anterior lobes looks like someone lying in a bathtub. Arms and leg coming out of the water. Arms and leg coming out of the water. And the hands extending into the posterior lobe. Okay. Then draw the mouth beneath the fingers. Oh, okay. Shoulders, feet. Oh yeah, I understand. I got that. I got that. Now show that there is duplication of the arms and legs in the posterior lobe. However, the legs are in opposite orientation. As mentioned, the somatotopic map of the cerebellum is in concert with its functional layout. The role of the spinocerebellar anterior lobe is to provide postural stability, which requires the limbs and trunk, and the role of the neocerebellar posterior lobe is to provide goal-oriented fine motor movements, such as those of the fingers and mouth. Only the most diligent anatomists did to memorize the cerebellar lobules. We include them here for completeness. But I think I will need it. Lobules. Okay. I think I will need it. Although not now, but I will need that. Nevertheless. Because I think it will be asked in the exam. How do you think about exams? I think it's good if you are exam oriented. You you revolve your motivation around a single exam. I've been doing that my entire life. And what happens when you don't have any more exams, or you have completed your final education or whatever? For me, whether it is a formal exam or informal exams in life or some anything in life that you are challenged with, it's an exam. Hmm. Ataxia. Okay. It looks like an onion. Seriously, it looks like an onion, very much like an onion. Okay, now we 10% of my battery. Oh, okay, no problem. primary fissure, posterolateral fissure. Insula, central lobule, declive, foveum, tuber, pyramis, insula, nodule, wing of central lobule, campanule, inferior, quadrangular lobule, H6, lobule, H7A, superior semilunar lobule, inferior semilunar lobule, H7B, gracilis lobule, H8, biventral lobule, H9, constant, H10, flocculus. Okay, so let's go move on to the next. Cerebellar pathways and midline structures. Here we will draw the pathways through the cerebellar peduncles, the cortico-pontocerebellar pathway, cerebellar midline structures, and arterial supply. Begin with the general organization of inflow and outflow through the cerebellar peduncles. Show and notate that the middle cerebellar peduncle, MCP, is an afferent pathway into cerebellum. It encompasses fibers that originate from pontine nuclei. Next, indicate that the inferior cerebellar peduncle, ICP, is also an afferent pathway into the cerebellum. It receives fibers from throughout the brainstem and spinal cord. Now show that the superior cerebellar peduncle, SCP, sends efferent fibers out of the cerebellum. In short, in regard to the inflow-outflow traffic of the cerebellum, the main inflow pathways into the cerebellum are the middle and inferior cerebellar peduncles, and the main outflow peduncle from the cerebellum is the superior cerebellar peduncle. Note the following major exceptions to these rules. Well, I have to use this. It's forbidden, but if it's cool, it's cool. Note the following major exceptions to these rules. 1. The anterior spinocerebellar tract enters the cerebellum through the superior cerebellar peduncle, which defies this peduncle's role as an outflow pathway. Select middle cerebellar tracts exit the cerebellum through the inferior cerebellar peduncle, which defies this peduncle's role as an inflow pathway. Specifically, These midline pathways are the fastigiobulbar fibers. The fibers from the flocculonodular lobe to the brainstem vestibular nucleus and certain monosynaptic cerebellospinal connections. Next, let's draw the corticopontocerebellar pathway. Indicate that the bulk of the pathway originates in the primary motor and sensory cortices. Corticopontocerebellar pathway. Indicate that the bulk of the pathway originates in the primary motor and sensory cortices. We exclude the lesser contributions from more wide-reaching brain regions. Nearly 20 million fibers are dedicated to the corticopontocerebellar pathway, compared to the nearly 1 million fibers are dedicated to the corticospinal tract. Now show that the corticopontocerebellar fibers first descend to the pontine nuclei, where they make their primary synapse. Next, draw the middle cerebellar peduncle and show that the pontine nuclei project across midline through the MCP into the contralateral cerebellar cortex. Then show that the cerebellar cortex projects to the nucleus dentatus, which lies deep within the cerebellum. Indicate that the dentate projects fibers out of the cerebellum through the superior cerebellar peduncle. Dentate projects here, which also cross midline and within the midbrain. At the level of midbrain. Okay. So, okay, pons, cerebellum, cortex, dentatus, and then we'll cross to at the level of midbrain. Inferior to the nucleus ruber, to synapse in the ventrolateral nucleus of the thalamus and also in nucleus ruber. Note that nucleus ruber projections typically originate from the globose and emboliform nuclei, which lie medial to the nucleus dentatus, whereas the thalamic projections typically originate from the dentate nucleus. Now show that the thalamus projects back to the primary motor strip to complete the corticopontocerebellar pathway. Next, let's draw the anatomy of the anterior cerebellum. Begin with one of the saddle-shaped cerebellar hemispheres. Next, label at the cerebellar peduncles. Inferior, superior, middle, and inferior. Now label ventriculus quartus. Next, include in our diagram the two components of the flocculonodular lobe. In the hemisphere, show the flocculus, and in the vermis, show the nodule. Here we see that the flocculonodular lobe lies in the anterior mid-cerebellar position. Cerebellar position. Not at the bottom of the diagram. Which is where our unfolded schematic of the cerebellum places it. Above the fourth ventricle, include the lingula, the slender vermian tip of the anterior cerebellar lobe. The lingula combines with the flocculonodular lobe to form the vestibulocerebellum. Wait. Okay. Next, include one of the paired cerebellar tonsils. We include the cerebellar tonsils because this paired midline structure is an important aspect of a common neurological condition, Chiari malformation. Okay. Lastly, let's show the basic arterial supply to the anterior cerebellum. Show that paired vertebral arteries feed into the basilar arteries. Basilar artery, which branches into the paired posterior cerebral artery, PCA. Then indicate that the posterior inferior cerebral artery, PICA, emerged from the vertebral arteries. Next, at the base of the basilar artery, show that paired anterior inferior cerebral artery, AICA, emerged. Finally, at the upper portion of the basilar artery, show that the paired superior cerebellar artery, SCA, emerged. Now show that on the anterior surface of the cerebellum, the PICA perfused the inferior cerebellum, AICA perfused the mid-lateral cerebellum, and SCA perfused the superior cerebellum. On the anterior surface, PICA inferior, AICA mid-lateral, SCA superior. Okay. Good. Oh, where is my here? One more image and you will be able to go to sleep. Oh, okay. Okay. Looks cool. Looks cool and neat. Diamond is unbreakable. cerebellar pathway. Okay, one more. If you can endure this, you'll be able to go to sleep. How many people have watched? Many. You forget you have to read something before that. Okay, might go to the bathroom. Just a quick 1 or 2 minutes and then we will continue. Because of this, they didn't receive the request. Is it good? No? Yes, it's cool. It wouldn't be funny if it fell on your face. Oh, I have to keep this. That's not spark joy. Cerebellar histology and circuitry. Here we will draw and learn the histology and circuitry of the cerebellum. Begin this diagram with a saddle-shaped cerebellar hemisphere. Where is my spectacle? Include along the surface a single fold called a folium. Okay. We see that the folding of the cerebellum into lobes, lobules, and folias allows it to assume a tightly packed, inconspicuous appearance in the posterior fossa. The cerebellum has a vast surface area, however, and when stretched, it has a rostrocaudal expanse of roughly 120 centimeters, which allows it to hold an estimated 100 billion granule cells, more cells than exist within the entire cerebral cortex. It is presumed that the cerebellum's extraordinary cell count plays an important role in the remarkable rehabilitation commonly observed in cerebellar stroke. Now indicate that the two main classes of cerebellar nuclei are the cerebellar cortical neurons and the deep cerebellar nuclei. Draw a magnified view of the volume in order to show the different cerebellar cortical cell layers. Magnified view of the volume. Okay. From internal to external, they are the subcortical white matter, substantia alba, the granule layer, Purkinje layer, the molecular layer. We still have just one. I thought I had bought. Wait, how many did I eat? How many cookies did I eat? Wait. How many cookies did I eat? The subcortical white matter, the granule layer, Purkinje layer, the molecular layer. Now let's look at the histological section of these layers. Show that the molecular layer primarily comprises cell processes, but also contains stellata and basket cells. The Purkinje layer contains a single layer of large Purkinje cell bodies. The granule layer is highly cellular. It contains granule cells, Golgi cells, and unipolar brush cells. Then label the substantia alba. Next, let's study the Purkinje and granule cells at a higher resolution. Indicate the cell body of a Purkinje cell. Indicate its neighboring cells' dendritic system. Which arborizes extensively within the molecular layer. Indicate a granule cell. Purkinje cells project a fine axon through the granule cell layer. Now let's draw the major features of a Purkinje cell. Draw a Purkinje cell. Show its cell body. Draw its nucleus. Indicate the nucleolus. Show its dendritic system. Now let's address the centrally located deep cerebellar nuclei. From medial to lateral, they are the fastigial, globose, emboliform, and dentatus nuclei. Medial to lateral. Show that together, the globose and emboliform nuclei are also known as the interposed nuclei. A classic acronym for the lateral to medial organization of the deep nuclei is "Don't Eat Greasy Food" for dentatus, emboliform, globose, and fastigial. Don't eat greasy food. Okay. Indicate that the deep cerebellar nuclei parse into specific functional modules. Fastigial nucleus plays a role In the vestibulo and spinocerebellum, fastigial nucleus plays a role in vestibulocerebellum and spinocerebellum. The interposed nuclei are part of the spinocerebellum. This is part of the pontocerebellum. Now let's show the flow of information through the cerebellum. Redraw the layers from inside to out. Substantia alba, granule layer, Purkinje layer, and molecular layer indicate that there are three main types of cerebellar afferent fibers. Afferent fibers. Climbing fibers, mossy fibers, and multilayer fibers, also known as monoaminergic fibers. All three fibers innervate both the deep cerebellar nuclei and the cerebellar cortex. Now indicate that the molecular and granule cell layers filter and temporally pattern information as it is transmitted to the Purkinje layer. Temporally pattern. Show that the climbing fibers are excitatory fibers that originate solely from the inferior oliva and pass via the contralateral inferior cerebellar peduncle to the cerebellum. Debate exists as to whether climbing fibers use the excitatory neurotransmitter aspartate or glutamate, but it seems the most probable that they use glutamate. Indicate that these olivocerebellar fibers are distinct in that each Purkinje cell is innervated by a single olivocerebellar climbing fiber. Note that this pathway represents the inferior arm of the triangle of Guillain-Moiré. Now show that the mossy fibers are excitatory fibers derived from diffuse cell populations within the brainstem and spinal cord. They, like the climbing fibers, mostly use the excitatory neurotransmitter glutamate. Lastly, show that the multilayer fibers are derived from neurobehavioral centers in the brainstem and the encephalon, such as the locus coeruleus, nucleus raphe, and the tuberomamillary nucleus of the hypothalamus, whereas the climbing and mossy fibers are unquestionably excitatory. The role of multilayer fibers is less uniform. They are considered monoaminergic because their cells of origin are generally associated with a single neurotransmitter type. The locus coeruleus is noradrenergic, the nucleus raphe is serotonergic, and the tuberomamillary nucleus is histaminergic. Next, show that the deep cerebellar nuclei send excitatory fibers to structures throughout the central nervous system. The majority of efferent information that leaves the cerebellum does so from the deep cerebellar nuclei, which act through the excitatory neurotransmitters glutamate. Indicate that the Purkinje layer, which is the sole recipient of this post-process information, sends inhibitory fibers to the deep cerebellar nuclei. Inhibitory Purkinje layers. Thus, the cerebellar cortex, acting through the Purkinje layer, is an important modulating force on the deep cerebellar nuclei. The Purkinje cells act through the inhibitory neurotransmitter GABA. Okay, you can draw now. Maybe I should turn off the camera now. Dispatched. Okay, my package has been dispatched. I ordered a whole cricket. Not a whole cricket. I mean a cricket snack. Yeah, it's a whole cricket, but it's a cricket snack. Let's see what else. Next, arriving tomorrow. Okay. Kokodi. Oh man, come on. Okay, look at this. I think we finished it on time. Thank you for everybody who joined. I don't know how many of you joined. And have a good night, have a good day, have a good morning. See you around.